Electrochemistry. Let us go through the important subtopics in electrochemistry. That is the topic 3 of electrochemistry. Please take down. In electrochemistry, the main topics to be discussed are take down 1. Electrochemical cells. 2. Galvanic cells. Electrochemical cells. 2. Galvanic cells. And within that, you have got some subdivisions. Then, third aspect is Nernst equation. Okay, you can write down in the always write down the topic 3 in the flashcard. Electrochemistry. We have electrochemical cells, then galvanic cells. Then, as a third topic, we'll be discussing about Nernst equation. Nernst equation. And where there are some subtopics also, but we are very keen on the main topics. Conductance of electrolytic solution. Conductance of electrolytic solutions. Then we have electrolytic cells and electrolysis. Electrolytic cells and electrolysis. Where we're discussing about the product of electrolysis, varieties of electrolysis. Then you have got the sixth topic, batteries. Batteries. And seventh, fuel cells. Eighth topic is corrosion. So these are the major subtopics in electrochemistry. We'll go one by one. So what are the major topics here? Electrochemical cells, galvanic cells, Nernst equation, conductance of electrolytic solution, electrolytic cells and electrolysis, batteries, fuel cells, and corrosion. And you can develop your own mnemonics for that so that you should be able to remember all those topics. Okay, right. Now, when you talk about electrochemistry, actually, that is electrochemistry deals with the transfer of energy. For example, it is because of the chemical reaction some electricity or electric current is obtained, and it is vice versa. Because of electric current, you can trigger the reactions also. So, it is the production of electricity from energy released during the spontaneous chemical reaction. What do you mean by this? A spontaneous chemical reaction naturally occurring. Naturally, it comes out. So, electrochemistry, that is the study of production of electricity. That is very important. So, main idea is production of electricity. And then that is from the energy released from the spontaneous chemical reaction. This is point number two. It is simply represented by delta G is equal to minus NFE, where, and this can also be called delta G minus delta G is equal to NFE also. So this delta G represents minus delta G represents decrease in free energy. Decrease in free energy. Decrease in free energy. So this is associated with the chemical energy. That is, free energy is nothing but it's called decrease in Gibbs free energy. This is called Gibbs, Gibbs, apostrophe S. Gibbs free energy. Decrease in Gibbs free energy. That represents the chemical reaction. And this represents the cell EMF, that is the electrical energy. So you can call it the electromotive force also. So this represents the electrical energy. So from this, chemical energy can be converted into electrical energy, as well electrical energy can be converted into chemical energy. Okay, so this is the very idea of what? The electrochemistry. And here, uh, electrolyte is a very important parameter here. Okay, electrolyte. What is electrolyte? Electrolyte. Electrolyte is the acid or base or salt that can conduct electricity in molten form or in solution form. So naturally, when you say solution, naturally it depends on the concentration also. So in that case, you should be aware of the expressions of concentrations also. It can be in terms of percentage or normality or molarity or molality. So based on the concentration, definitely its conductance parameter will be varied. So that is why we call electrolyte. Electrolyte can also be called electrolytic conductor. Electrolyte can also be called electrolytic conductor. So this electrolytic conductor is nothing but ionic conductor. Ionic conductor. Hence, we can classify this conductor into two types. One is metallic conductor, another is ionic conductor. Metallic conductor, here electrons are responsible for conductance of electricity. In the case of ionic conductor, ions are responsible for conductance of electricity. So it can also be called electronic conductor. Electronic conductor. and this is called ionic conductor, and that is also called electrolyte or electrolytic conductor. So here it is nothing but copper wire or silver wire or iron, etc. Whereas in this case, it can be an acid or base or salt, but it should be in the aqueous form, that is solution form, or molten form. It should be in the liquid form. You can take even HCl, H2SO4, NaOH, KOH, NaCl, KCl, etc. But they are ionic basically. And in the case of conductance, let us consider conductance. There is an opposite term called resistance. We already discussed in physics that resistance is directly proportional to length of the conductor. Let me consider this conductor of length L and another conductor of area of cross section A cross section. So when the conductor is wide, it is inversely proportional to area. So that is why we can combine to form L by A. It means that is R is equal to, you can introduce the proportionality constant, that is specific resistance or resistivity into L by A. So when you consider this resistance, its unit is ohm. It is represented by omega. Whereas resistivity is indicated by, we can derive the equation. So what is R? That is equal to rho into L by A. So you can retain this rho, therefore RA by L. It means you have got ohm meter squared divided by meter. So you can cancel it. So you have got the unit ohm meter. So this is also represented as ohm meter. Sometimes if it is represented as centimeter, then you can call it ohm centimeter. Okay. Actually, the resistance is proportional to the dimension. So that is some shape size are there. So it is dependent on the, that is amount, that is how much, how long, how big. So this is a in, extensive property, because extensive property is a property that depends on what? Quantity. Whereas this one is a qualitative one, so intensive property. It means it is constant. It is not variable with respect to the length and any other dimension. It is a natural property. And the reciprocal of resistance can be called conductance. Similarly, it should be represented in small letters C. C represents conductance here. R represents the resistance. So you have this reciprocal of R, that is nothing but resistance. Similarly, you have got the reciprocal of rho, that is called kappa. Okay, that is called conductivity. So this is called kappa, means conductivity. And this rho is called, this is a rho. resistivity. So we know already the ohm unit is ohm meter. So in that case, what is kappa? 1 by ohm meter, OHM meter. So it means ohm inverse meter inverse. That is the unit of kappa. And these are all concerned with the regular conductor, metallic wire. But in the case of solution, you need to introduce another parameter that is called equivalent conductance because it depends on the concentration also. So you have to represent in the case of conductor, for example, let me consider a beaker where you have dipped two electrodes like this. So the distance between the two electrodes can be taken as the length of the conductor. Here we talk about the bulk of the solution, that is the ionic conductor present in between the electrodes. So that is taken as the length of the conductor here. So the interelectrodic distance. So here L is nothing but interelectrodic distance, where the ionic conductor is very active. So we represent by this. And A means which is nothing but the area of this liquid conductor that reflects the surface of electrode, and that is why here A is taken as electrode surface area. And we have dipped the electrodes in electrolyte. We simply represent, for example, if copper electrode is dipped in copper sulfate solution, it is represented as Cu2 plus, Cu slash Cu2 plus. Similarly, and we know something about the that is some deposition or dissolution takes place based on the nature of the electrode. When you talk about the electrode, this is a metallic electrode. We have got gas ion electron also, but let us confine to metallic electrode. So this electrode is dipped in an electrolyte. So that is represented here. So copper as wire or rod that is dipped in an aqueous solution. That is, it can be copper sulfate solution. So this is the way we represent. So this electrode definitely we have anode and cathode. At anode, oxidation takes place. At cathode, reduction takes place. At anode, oxidation takes place. At cathode, reduction takes place. And once again, we should be aware of the redox reactions. For example, oxidation and reduction. This is a simple way to represent oxidation. Addition of oxygen, removal of oxygen. And then addition of removal of hydrogen, addition of hydrogen. Otherwise, removal of electron, de-electronation is oxidation. That is loss of electron. LEO is oxidation. Then gain of electron. That is GE or Leo, you can say. Or you can also call it oil. Oxidation is loss of electron. Reduction is gain of electron. Oil rig. Like that you can memorize. Then here you have the increase in oxidation number. So here you have decrease in oxidation number. The simple way of remembering this is, for example, Fe2 plus becomes Fe3 plus. Ferrous becomes ferric by loss of electron. This is the best way. So there is an increase in oxidation number. The reverse reaction, that is Fe3 plus E, that results Fe. That is the gain of electron. So it is reduction. And oxidation is an anodic process because it occurs at the surface of anode. So you can call it anodic reaction. Whereas the reduction takes place at the surface of cathode, so it is called cathodic reduction. Okay, cathodic reduction. Now we have anode oxidation, cathode reduction. So this can be better represented like this. For example, when you have two electrolytic baths, you have got one electrolytic bath and another electrolytic bath, and you have got the electrolyte here, another electrolyte here. So this is the cathode bath and this is the anode bath. So the electrolyte are kept in cathode bath or anode bath. So suppose if I fix anode here and here it is cathode. So this electrolyte is called anolyte. So the electrolyte kept as in the anodic compartment can be called anolyte. Similarly, this is catholyte. And you can trigger the reaction by connecting this to anode and cathode. And the circuit should be completed, is it not? So in order to complete this circuit, we need to introduce a salt bridge like this. This is called salt bridge. Salt bridge is nothing but a PA type, that is inverted U tube. Initially, we take the pipe like this and we take agar agar, it's a kind of starch you can say, which forms a gel, agar agar, Agar, agar agar. Then that is you got a KCl, that is in the solution form. So we have to heat it and dissolve it so that it forms a liquid. That liquid is poured here. And once it reaches the room temperature, it becomes like a gel so that you can suitably invert it and keep it as salt bridge here. So that communicates between these two compartments, anolyte and catholyte. And at anode, as we know, oxidation takes place. At cathode, reduction takes place. Now let me consider any electrode as you are familiar with this. Let me take this is copper electrode. Dipped in the electrolyte is copper sulfate, CaSO4 at certain concentration as aqueous solution. Similarly, you've got silver nitrate here, so you can put silver nitrate, that is electrolyte, NO3. Then you've got silver electrode. So this can be represented as a cell. How? Now connecting this copper that is dipped in copper electrode, copper solution, copper electrode dipped in copper solution. And this is a solid and this is an aqueous solution. And then this salt bridge is indicated by double slash. Then you can put, you have to reverse it, that is Ag plus as a solution, that is aqueous form, bar or slash Ag. So this is the cell representation. So just by looking at this cell, you can say this is connected to anode and this is connected to cathode. Okay, this is connected to cathode. So we can easily establish the cell like this. Okay, right. Now I have given some simple idea about the electrochemical cell. And now let us see the types of cell. So here you can find a Daniel cell. So this Daniel cell is capable of converting chemical energy. Okay. So the chemical energy actually is the cell converts the chemical energy liberated during the redox reaction. Liberated during the redox reaction. What do you mean by that? And this galvanic cell can also be called the voltaic cell. So here it has got the electrostatic and electric energy, not electrostatic, electric energy with the value of electric potential that is equal to 1.1 volt. So this is capable of delivering such voltage, right? So this is the electrolytic cell is the device that is capable of converting electrical energy to carry non-spontaneous chemical reaction. Please note on this. I said there are some spontaneous reaction that is responsible for creating the electrical energy. So in this case, what we are doing, we can force the chemical reaction to happen by introducing the current in this. Okay. So that is why here electrolytic cell is the device for us for using electrical energy to carry non-spontaneous. So non-spontaneous means that is I would like to explain this spontaneity. When a reaction is capable of taking place automatically, then delta G is supposed to be minus. So when you have any chemical reaction has such type of negative value, you can say this is the natural reaction or spontaneous reaction. Okay, spontaneous reaction. There are so many concepts, but I would like to stress on two important aspects. So for any chemical reaction to happen, there should be negative. That is the change should be. I'm talking about the change. What do you mean by this? For example, let me consider A plus B gives C plus D. So it means here the sum of reactant and here the sum of product. Okay. So the G, I mean the Gibbs free energy, the sum of Gibbs free energy of reactant, the total. Similarly, the sum of Gibbs free energy of the product, you can call it GP. So delta G means summation of this GP minus summation of this GR. And if it consists of n number of products, you can put NP also, here also NR. Okay, it depends on the number of moles also, but roughly you can take. So this free energy, when it is decreasing, what do you mean by this? It means when you will have the minus delta G value, can anyone tell me? When GP is more than GR or GP is less than G? When GP, okay, the summation of n number of product of GP value is less than the summation of n number of product of reactant of GR. Okay. So naturally this gives you the negative value. Do you understand this? Okay. Right. So what does this gives the free energy? In thermodynamics, it's much talked about. Free energy is nothing but the energy available. That is available form of energy, you can call it simply. Available form of energy. That can be called free energy. Okay. And actually that is this is one of the thermodynamic properties. What are thermodynamic properties? We have pressure, volume, they are called TDP, take down, TDP, thermodynamic properties, pressure, volume, temperature, and then you have got entropy, internal energy, then Gibbs free energy, and enthalpy. Then you can call it Helmholtz work function. That is work function, you can call it. Okay, F or A. So these are all thermodynamic properties and they are closely associated with the chemical reactions. Okay. So according to thermodynamics, without temperature change or without heat involvement, nothing will take place. Okay. So for any reaction to occur, there should be some change in temperature. I mean, you should not call it temperature, heat, because temperature is the measure of hotness or coldness. Okay, right. So this is the available form of free energy, and that is why we call it delta. And this is one of the conditions for the spontaneity. What do you call it? Spontaneity of chemical reaction. Spontaneity of chemical reaction. Similarly, you have one more term that is increase of entropy. That is delta S. There should be entropy increase so that these two are that is very important in determining the progress of the reaction. So let us talk about in detail in thermodynamics. But anyway, you should be aware of these terms associated with the chemical energy, that is thermodynamics in this case. Now let me come back. So here you just look at this diagram and you've got the zinc rod dipped in what is that? Zinc sulfate solution. And you've got copper electrode dipped in copper sulfate solution. So here there are when you dip the electrode in an appropriate electrolyte, there are two kinds of reaction take place. For example, when a metal is dipped in its electrolyte, okay, so there are two types of reactions taking place. One is metal can be converted into that is ion like this by a removal of n number of electrons. So what do you call this process? Electrons are lost, loss of electron oxidation. And the reverse can also happen. For example, Mn plus Ne gives M. It means now let us look at this is reduction. Okay. So in this case, in the case of a zinc, okay, in the case of zinc, if it is anode that is oxidized, oxidation takes place. So what kind of reaction has taken place here? Oxidation, because zinc has become zinc 2 plus. It means that is the electrons are moving up by releasing the what? Mn plus to this ion. Are you able to follow in the bar? So there are two things happening here. When you dip an electrode, okay, either from the metal it can go into the solution. Okay. So from the metal, it goes into the solution means what? M becomes Mn plus. Do you understand this? Okay. That is metal is getting dissolved. Is it not metal? So some quantity of metal is dissolved, lost here, and they go into the solution, the bulk of the solution. And what about the electron? The electrons will be lost. And where they are moving? They are moving towards along the wire. So that is why the direction of electron flow is shown here. Are you able to follow this? So this zinc is releasing zinc 2 plus ion. That is a metallic dissolution, right? Suppose before starting this experiment, let us weigh the electrode. Let it be M1. After some time, the metals are dissolved here. The zinc metal is dissolved and weigh the metal once again, that is M2. And definitely M2 will be less than that of M1. Why? Because there is a loss of metal as metal ions and they have gone into the solution. But what about the electron? The electrons are moving up and they are responsible for flow of electron. What do you mean by flow of electron in this direction? That is nothing but current, but it acts in the opposite way, and that is why it is indicated here current as the opposite direction. Do you understand this? Then, now let us talk about this one. So here what happens? These electrons are coming inside and coming here. So the copper ion from here, copper ion from the bulk of the solution, they try to deposit on the electrode by accepting the electron or it will follow. So what happened here? That is, this is at anode. At cathode, what occurs? This is a metal electrode. Now we have tip. So here the transfer of electron, I mean the metal transportation occurs like this. It means that is M N plus accepts, that is copper 2 plus accepts number of electrons from the wire to give, from the rod to give metal. So that is deposited here. Now let me say this is M1 and M2 is a later weight. Similarly, you have M3 and M4. Now look at this. Here M2 is less than M1, right? And here M4 is greater than M3. Do you know why? Here dissolution takes place, here deposition takes place. So from this, you can understand that there is a mass transfer. There is a loss of mass. And Faraday, he was able to establish a law based on that. Okay. So one thing is pretty clear here. There is some mass loss and that mass must be accounted. How we can account for that? So that is governed by Faraday's law. Take down. So Faraday's law of electrolysis. Electrolysis. So here he said, I'm talking about only the first law. That is the amount of substance, that is M, either dissolved or deposited, is proportional to how much charge is given here, Q. And we know Q is nothing but IT, how much current is passed in a given time. So it can be M is proportional to IT. So we need to introduce a constant and that is called electrochemical equivalence. So that is known as C into. So this is called Faraday's first law. I'll explain later about the second law, but to start with, I would like to give some exposure about this Faraday's law. So one, and this can also be represented like M is equal to Z into Q. That is also correct. And Q is further expanded as IT. So you can have both formula. Okay. Now let me come back again. So here you have the metal, that is zinc metal. This is copper and that is connected through a salt bridge. So you are able to get some amount of electric potential and its potential is around the 1.1 volt. So this is the rough idea I'm giving here. So the electrolytic cell, what is the role? It converts the electrical energy to carry out the non-spontaneous chemical reaction. That is, electrical energy is converted into chemical energy, right? Are you able to follow? Now look at this diagram. So we have got diagram 3.2. So in 3.1, I explained about the Daniel cell. And what is Daniel cell? It consists of anode and cathode. Zinc as anode that is dipped in what? Copper and zinc sulfate. Here, copper is dipped in copper sulfate and that is connected through sulfate. So, Daniel cell having electrodes of zinc and copper dipped in the solutions of their respective salts. That point is clear. And since this Chemical energy is what do you call that is happened. It has happened because of current. Okay, some voltage. Okay, by applying certain amount of voltage, say about if you apply 1.1 voltage, you are able to get this equation, this reaction. So it means it has got certain galvanic. Galvanic means something associated with the current. Volta means potential. Okay. So galvanometer means what? It is a device that measures current. Voltmeter, it is a device that measures voltage. That's all. Okay. So the respective that is name is given here. So galvanic cell or voltaic cell. So the Daniel cell can also be called. It is the Daniel cell. That is nothing but voltaic cell or galvanic cell. Yes, what's it do? Meter also is responsible for the measuring time. Okay, you have got galvanometer, you have got a meter. Okay. Then salt bridge that connects between the two electrolytic bar. It will carry ions, but that is balanced accordingly because it consists of K plus and Cl minus ion. So KCl is there. So it balances, acts as a supporting electrolyte, you can say. It supports the electrochemical reaction. Then, uh, because for any circuit, it must be completed. Okay, there must be some connecting point, and the circuit should be closed. Otherwise, the reaction will not take place. Okay. Then, in this case, now you can see the potentiometer here. So it is around a 10 meter and this and it has got 10 folds of 1 meter each. So based on the you have got this is known, the wire itself is called the resistance, you can call it. So by keeping at various length, you can vary the potential. So that you have studied already under meter bridge and potentiometer in current electricity, is it not? So in physics we have already studied. So this is a potentiometer that is responsible for measuring the current also, potential. So, and by keeping the jockey at various position, you can change the potential. By changing the resistance, you can change the potential also. Okay. So likewise, by changing the key position, you can change the potential and alter it and conveniently fix the potential. Okay. So now look at it. When the external EMF, okay, E external means external EMF, is less than 1.1 volt, the electrons flow from zinc rod to the copper rod. So when it is less than 1.1 volt, the electrons move from here to here. That is from zinc to copper. And hence current flows from copper to zinc. That is the volt. That is the vice versa. Okay. This is one important point. Now listen. When the voltage, that is external voltage, is equal to 1.1 volt. Look at this diagram. When it is equal to 1.1 volt, it means there is no current because no flow of electrons or current. So it means there is no chemical reaction taking place. Okay. It means no chemical reaction taking place. Okay. Right. And look at this. Now, when the external voltage, EMF, is exceeding 1.1 volt, what happens here? The electrons flow from copper to zinc. It takes the reverse direction. Okay. It takes the reverse direction like this. That is copper to zinc. In that case, current flows in the opposite direction. Is it not? So electron flows from copper to zinc. Copper to zinc means what about the current? Current flows from zinc to copper. It means now zinc is deposited at the what? Zinc electrode and copper is dissolved here. So there is an interchange of the poles here. Are you able to understand this? So here it acts as a potential or positive potential. That is oxidation takes place here. I mean reduction takes place here. Deposition means what? Deposition means reduction. Is it not? Remember that you are supposed to. You just have this. Always go through the notes. What is this? This is deposition. Huh? If it is deposited, what do you mean by that? That is nothing but it acts like a cathode, so reduction. If it is a dissolution, it is oxidation. So you can mention here itself oxidation, reduction. So you can find the reverse phenomenon here. So previously I told here dissolution takes place. Then dissolution takes place, and here deposition takes place. Okay, so current moves in this, I mean, electron flow moves in the way, current is in the opposite direction. But here it is in the opposite way. Okay, are you able to follow? But you can look at the electrode also. You just look at it. Now it becomes positive. Are you able to follow? Okay, there is a change of potential here. Okay, so when you draw this diagram, you have to be very careful about the circuit, the direction of flow of current, the direction of current, and also the polarity of the external EMF also. So all these things you should be noted down. Okay, so this is regarding your electrochemical cells, that is Daniel's cell. Now let us talk about another galvanic cell, galvanic. So here it is the cell that electrochemical cell that converts chemical energy of a spontaneous redox reaction into electrical energy. Please note down. Okay. So here Daniel cell is discussed earlier. In one such cell, the reaction occurs like this. What happens here? That is zinc plus Cu2 plus gives Zn2 plus copper. So how it happens? Now let me write here. This is the case with the Daniel cell. Daniel cell, what was the reaction? Zn, that is S plus copper 2 plus aqueous becomes zinc 2 plus aqueous plus copper. Okay. So here zinc becomes zinc 2 plus by oxidation, right? So loss of electron. Do you understand? And what about copper? Copper becomes copper 2 plus becomes copper. That is the reduction. Okay. Now at anode here, what kind of reaction has taken place? Zn becomes Zn 2 plus plus 2 electron. That is oxidation. At anode, at cathode, what occurs here? Cu2 plus accepts 2 electron to become what? Then Cu. Okay. So this is reduction. Now we can combine these two reaction and remove the electrons so that you are able to get zinc plus copper 2 plus gives zinc 2 plus plus copper. So that is the reaction. Okay. So actually this is the, we already know that these are called anodic reaction, cathodic reaction, and this is the electrodic reaction, that is electrochemical cell reaction. Okay. So what about this? This is anodic reaction, this is cathodic reaction, and this is electrochemical reaction. How is it possible? By the combination of two half cells. What are those two half cells? Zinc slash Zn2 plus copper 2 plus slash copper. Okay. And that is why the electrochemical reaction is nothing but the redox reaction. So do you understand this concept? Okay. Then, and there is a particular potential required for this, and that is known as standard potential. Take down. For example, when you dip an electrode in an electrolyte, okay, so that arises the potential that is called electrode potential. Suppose zinc is dipped in zinc 2 plus ion. Okay. And this is the oxidation potential. So it should be represented as zinc oxidation potential. If it is carried out at the standard state, that is STP, standard temperature and pressure, this is known as zero, not you can put. So E naught oxidation potential. So standard oxidation potential. So what do you call it? Standard oxidation potential. Okay. Now let us uh, assume that we have got the copper. So copper is dipped in copper sulfate solution, right? Copper is dipped in copper sulfate solution, Ca2 plus. Okay. So, and as I already mentioned, this can be represented by zinc slash zinc 2 plus. And this is by electrode that can be represented by Zn bar Zn 2 plus, right? And what about this? This is represented as, that is copper. This is a reduction potential. Okay. So E naught reduction potential. So this is represented as E naught copper 2 plus slash copper. Okay. This is known as reduction potential. Standard reduction potential. Audible follow? So we can actually, what has happened here in the case of combination of these two cells, I already discussed by combining anode and cathode, you are able to get what? A chemical cell EMF. Likewise, when you combine two electrode potential, you can have cell EMF. Therefore, cell EMF, E means cell EMF, is nothing but, that is Zn, Zn2 plus, plus copper 2 plus copper. Okay. But when you look at this, as far as our Indian standards are concerned, we go by the reduction potential only. We go by reduction potential. So there is a complete list of all this reduction potential at the standard state, that is a standard temperature and pressure for various electrode assembly, and that is called electrochemical series. You can find here. So this is called the electrochemical series, where you can find everything is given in reduction. So addition of electron is what? Reduction. So when you look at hydrogen, its value is zero. So above zero, you can find positive value of reduction potential. Below hydrogen, you can have the negative reduction potential. What does it indicate? When you say negative reduction potential, naturally those electrodes have the tendency to undergo or act as anode only. Okay. Therefore, that is, this electrode potential in this case can also be represented in terms of reduction potential. That is this oxidation. Okay. So I already told, that is, this can be, let me introduce two equations here. E is E cell, you can call it, is equal to E naught, okay, E naught oxidation potential plus E naught reduction potential. This is one equation. But as I already told you, that is the when you represent the oxidation potential in terms of reduction potential, it takes a negative value, the opposite. Okay. So it means, now let me consider this E cell. Follow me very carefully. How to represent the oxidation potential? E naught Zn bar Zn2 plus, right? How to represent the reduction potential? That is E copper 2 plus bar ion first followed by copper. Okay. So I want to represent, so this is oxidation potential. This is reduction potential. Now I want to indicate this oxidation potential as a reduction potential. Very good. So in that case, what am I supposed to do? I have to introduce the negative value and put that is Zn2 plus bar is Zn. Okay. So do you understand this concept? So plus and you have E copper. So in this case, both are reduction potential only. Do you understand this? So I'm giving this a EMF in terms of both reduction potential. And where is the uh, copper present, that is oxide, anode present. Anode should be always represented or given on the left side by cell convention. So you could have seen here, I already told, that is anode should be represented on the left one way. So in the cell representation, initially I would have given, okay, where is it? So here I have given anode always on the left. Please note down. Cathode always on the right. Okay. Now here you can call it a right electrode and a left electrode. Okay. So in that case, how we can proceed? Which is present on the right side? Cathode, and that is why we take E cell simply after writing this electrochemical cell notation. Simply we write E right minus E left. Okay, please note out this. Okay, so this is very, very important. But when you combine the equation, you will be introducing this one. We are combining as per plus. Okay, but when you go by the electrochemical cell notation, you have to adopt this formula. Okay, so these two formula are very, very important. Okay, so when you work out some problems, you may get some confusion. So in advance, I am explaining about this. And then, so here you can find now, what about, let us compare this. You have got, let me take this silver. Okay, what is the value of silver? Ag plus E gives Ag and its value is zero point 0.8. So electrode potential is zero point 0.8. What is that electrode potential? How to represent that? That is E naught, then Ag plus Ag is 0.8. Okay, is it clear? Right. This is the standard reduction potential of silver. Okay. Now let me combine this copper. Okay, so copper 2 plus 2E gives copper. So in that case, that is E naught Cu2 plus slash Cu is equal to, now listen to me, 0.34. Okay, so this is the 0.34 volt. This is 0.8, this is 0.34 volt. Okay. Now, what you are supposed to do, based on the chemical series, you should be able to establish the cell notation and get the cell EM. Can you do? Let us try. Now, just by looking at these two values, you know which electrode potential, which reduction potential is higher. Silver. Silver. So it means that its reduction, that is reduction means cathodic nature. So this cathodic nature is more than that of copper. Are you able to follow? So this is naturally occupying which electrode? Cathode. Okay, so where the cathode should be kept? The cathode should be kept on the right side. So this is the right electrode. So we can indicate like this. More reduction potential means more cathodic behavior. So R, this is the right electrode and this is the left electrode. Immediately you can say. Now can we establish the electrode cell notation? Left electrode is copper. So how to represent that? Copper and then tell me. Yes, copper 2 plus and then double slash put equals and here Ag plus Ag. Yes. And this is equals. We are established. Now, this is the left electrode. This is the right electrode. We know left electrode is anode. Right electrode is cathode. Okay. Now, what is the value of this electrode potential? For copper, it is 0.34. Okay. Volt. And for silver, 0.8 volts. And now, what is E cellium of ER minus EL? Therefore, what is ER? 0.8 minus 0.34. So, what is the value? 0. So, 0.54 voltage. Now, by combining, listen, by combining By combining this copper and silver electrode, we are able to get 0.54 volt. Got it? So what is the cell EMF obtained? What is the cell EMF obtained here? It's correct as 0.54. Tapasula. 0.8. Tapasula. 3, 4. அப்படின்னா 6. இங்க என்ன வரும் 4. Okay. You have to be very careful. Okay. Right. Now listen. So zero point 0.8 minus a 0.34 that gives 0.46. The eyes will cheat you like anything. So you have to be very careful. Then E cell is this much value. Okay. Suppose if you interchange the electrode, what will happen? That shows negative value. So if the E cell value is negative, that the cell is not possible. Okay. So this is not spontaneous. You can prove this. Okay. Then, so from this you can study the spontaneity of the reactions also, okay, and the feasibility of the cell combinations. Now listen, and now let us work out on the chemical electrochemical reaction also. So what about this anode? Anode is the oxidation. Let us work out like this. At anode, take down. At anode, oxidation occurs. Okay. So oxidation, what is that at anode? Copper is anode. So copper becomes copper 2 plus plus 2E, right? And what's this electrode potential? 0 point, and this should be indicated as oxidation potential. Minus. So E off. Okay. So here is, tell me, minus 0.34 volt. Then what about cathode? At cathode, tell me, Ag plus E gives how much? Huh? Ag. Okay. So what about this potential here? 0.80. Okay. This is reduction. So 0.8. Now in this case you can combine so that it is nothing but zero point 0.8 minus a 0.34. Once again you can have the cell reaction. Okay. So here you had to multiply by 2, 2, 2. Okay. Am I right? So you will get copper plus 2E can be cancelled, and then 2Ag plus gives copper 2 plus 2Ag, for which the cell reaction is how much? Not E cell is equal to 8 minus 34 means 0.36. Okay. 34 or 36, 36. So 36 voltage. Okay. 46, not 36, 46. You get the same result, provided that is in this case you have to change the sign. Okay. So when you use right minus left, you can use straight away the reduction potential. If you use plus, that is oxidation plus reduction, then you have to accordingly change it. So shall I give you one more equation like this? With respect to the values given in standard electrochemical potential, that is electrochemical series, combine a cell with aluminum and nickel. Try this. You can try on both. Anyone? Do it on the board. And anyone do that? Values you can refer. Values reduction potential of zinc is zinc, aluminum and nickel. Aluminum and nickel. Nickel 0.25 minus 0.25 minus 0.25. Aluminum minus 1.66 volt minus 1.66 volt. Someone can come and do it on the board. Come fast. Come quick.